Last week, you should have read through the BBC Bite-sized pages on electricity, and I just wanted to go through a couple of things before you move on to magnetism next week. When we talk about electricity, we are referring to an electric current, which is a flow of electrons around a complete circuit per second. There are different types of circuit, and I've set some up here. The first is a simple circuit. For the bulb to go on, it needs to be complete. So if I remove a wire or turn off the power pack, the bulb will go out. So if I turn off the power pack, the bulb goes out, switch it back on, the bulb lights up again. Or if I remove a wire, the bulb goes out, pop the wire back, and the bulb lights up again. If the circuit is not complete, the electrons can no longer flow and the light bulb cannot turn on. I can represent this circuit in a drawing using some of the symbols that you drew out last week, and it would look like this. Here is the symbol for a bulb, here is the symbol for a battery or a power pack, and the lines represent the two wires. Other types of circuit include this series circuit, where all the components in the circuit are set up in a single loop. If I follow the loop with my splint, you will see that it is a continuous loop circuit. So if I start at the power pack here, follow this wire down to one light bulb, then follow the second wire along to another light bulb, and then the third wire goes straight back to the power pack. It is a continuous circuit, there are no breaks in this circuit, and both light bulbs are lit. But this is called a series circuit. This circuit is known as a parallel circuit. It is made up of more than one loop. If I move my splint around the circuit, I can't cover it all in a single loop. I either follow from the power pack along this way, down here to this light bulb and back again in one large loop, but I haven't gone via this light bulb here. If I go via this light bulb here by following this wire down onto this light bulb and then along here and back up again, that's a loop, but I've missed this light bulb out. So this circuit is a parallel circuit. It has more than one loop in it. This piece of equipment is called an ammeter, and it can measure the current that flows through the circuit. Now we measure current in amps using a capital A. In a series circuit, wherever I place the ammeter, I should get the same reading as the current flowing through the circuit remains the same. So I've placed two ammeters here on this series circuit, and although the reading is changing ever so slightly, it is changing the same for both of these ammeters. So they're in two different positions on the series circuit, but they are measuring the same amount of amps. Now, as it shows in the textbook, with a parallel circuit, the ammeters in positions 2 and 3 should show the same reading, and the ammeters in positions A1 and A4, they're actually measuring the total current flowing through the circuit. The currents in all the branches of a parallel circuit, that's these two here, they should add together to make the total current, which is shown by these two ammeters here. And the total current should be double that in each branch when you have got a two-looped parallel circuit. So if I take you over to my parallel circuit, we'll see if this is the case. And you can see here that the total current on each side is flicking between 0.39 and 0.4 on that side. The same thing is happening over here. So our total current in this parallel circuit is somewhere between 0.39 and 0.4 amps. So on each branch, it should be half of that. So if we look here at one branch, we will see that indeed the current is running at 0.19 to 0.2 amps. And here on my other branch, I have the same. So 0.19 to 0.2 amps, half of the total current. Something else you may have heard of are volts. Now, volts are measured, they're a measure of something called the potential difference. This is a measure of the push of a battery or an energy source, such as a power pack, and also a measure of the energy that they can supply. The piece of equipment we use to measure volts looks like this. It's very similar to the ammeter that I just showed you. The way that you can tell the difference is this one has a V and the other piece of equipment had an A. So these are two circuit drawings of the two circuits that I've had set up. And if you were to measure the potential difference in those, it would go something like this. So in a series circuit, the potential difference across each component should add up to the potential difference across the battery. So here's the battery shown here in this diagram. The V in a circle represents the voltmeter. So if you were to measure the voltage running across the battery, it should be the same as the total potential difference across these two components. So these two are bulbs and they would measure 3 volts each. Add them together, you get 6 volts. Okay, so each component adds up to the potential difference across the battery. In a parallel circuit, you can see from the diagram you have the battery here, and then you have one light bulb on one branch and you have another separate light bulb on a second branch. If you were to measure the potential differences in this circuit, you should notice that the potential difference for each component, so for each light bulb, is exactly the same as that for the battery. So our voltmeters should read exactly the same amount across the two light bulbs as they do across the battery or the power pack. I hope that helps, and if you're missing the classroom N4, I'll just give you a quick view. There we go, my flask of tea. And I'm going to set you some worksheets to see if you are following this correctly. I hope it has helped a little bit. Take care, everybody.